Hello and welcome back to another Chem 1 video. And in this video, we're going to explore a little bit more the energy changes that we saw in the driving forces video. If you haven't watched the driving forces video, which was the first video that was included in this lesson, please go back and watch that driving forces video now so you have a better understanding of what's going on in chemical reactions. So what we saw in that video was that there are two kinds of reactions that give off heat and reactions that take in heat. Now, we talked about heat the other day, and heat being the exchange of energy. The question is, where is that energy coming from? And where that energy comes from is something called the enthalpy change in a reaction. Now, on the y-axis, let's add to the y-axis. This is not just energy, but this is chemical potential energy. Now, chemical potential energy just means how much energy do we have in the bonds that when we rearrange those bonds, we can either give off or take in energy from the surroundings. So in our universe, and I don't know why I just went all the way down there. In our universe, we have two regions. We have the system. The system is what we are studying, and the surroundings are everything else. Okay, so we've got everything. And, when we talk about the universe, we are literally talking about the entire universe. Now, in the next lesson, we will learn how chemists actually try to limit that universe to something that's a little bit more manageable. But for now, you can think of the universe as being everything. And so we're going to talk about reactions as being the system. So the reaction is the system that we're looking at. And the surroundings are going to be the air or the water or maybe you around that reaction, sensing what's going on with the reaction. And what enthalpy is defined as the heat content of a system. In other words, where can you go when you do a reaction? Can you go up? Can you go down relative to your products? And we're going to keep in mind that because of conservation of energy, if one loses, the other gains energy. And it has to be the same amount of energy being gained or being lost. Otherwise, we're going to violate conservation of energy. So in this diagram here, we have reactants starting off with a higher chemical potential energy than the products. These products are actually more stable. And this is a definition of stability. As you go down in potential energy, it's more stable. It's very similar to having a ball on a hill. So here's a ball up on top of the hill. And if we kick that ball downhill, that ball comes downhill, and it will be more stable down at the bottom of the hill. And chemists actually do talk about these reactions as being downhill or uphill. Downhill being a favorable, so this is a favorable way of going because we're ending up with something that's more stable. Now, what's going on here is that the reactants start off with higher energy. So that means as the reaction goes along, and the reactants lose energy, we have a negative delta H. So the energy of the system goes down. The energy of the system goes down. Where does it go? Well, it goes into the surroundings. So to the right here, I'm going to draw a little Erlenmeyer flask. This is my representation of the reaction taking place. And here's the system, whatever the reaction is taking place, and surrounding that system. And I'm going to use red now because it's going to, you'll see in a moment. This is our surroundings. This undefined whatever else there is. Since the system is going down, that means energy is coming out. So energy then is coming out of the system. Well, where does it go? It goes into the surroundings. When it goes into the surroundings, that means the surroundings gain energy. So the energy of these surroundings goes up. But what kind of energy is going up? Not chemical potential energy, the energy that's coming out, transferring as heat. So that's our Q being transferred, is becoming chemical energy. So we're starting off as chemical potential energy, and we're ending up as thermal. We call that thermal energy, thermal kinetic energy. And the temperature, the kinetic energy goes up, and the temperature goes up. So this is why exothermic reactions, reactions that evolve heat, are going to make the surroundings hotter. Now, in the video that you saw, they put some numbers on it, and the numbers they put on this was 100 kilojoules per mole of reaction down here, and I think they had 400 kilojoules per mole of reaction, up here. And so the delta H, the change in enthalpy, we can never measure absolute enthalpy, but we can measure the change in enthalpy, which is actually sometimes called, the change of the enthalpy is sometimes called change, let's see, write this down here, change in enthalpy is the heat of the reaction. And it can be positive or negative, or in odd situations can also be zero. So the delta H is always going to be wherever we started, so that would be the potential energy of the, wherever we ended up of the product, minus the potential energy where we started, the reactants. In this case, then, it's going to be 100 kilojoules per mole minus 400 kilojoules per mole, or negative 300 kilojoules per mole. So this would be a reaction that gives off, it's negative because as you're seeing in the diagram, the potential energy of the system is going down. It's exothermic because the energy is going out of the system into the surroundings and heating up the surroundings. Down below, we have the energy diagram for an endothermic reaction. So we've already discussed most of the terms. Again, let's write in here chemical potential energy. And actually, blue is a good color now, as you'll see in a few moments. Chemical potential energy, we start off low. And we're going to start off at, in the video, they said 200 kilojoules per mole of reaction. And we got up to 600 kilojoules per mole of reaction. So go ahead and write those numbers in there. Now, this is driving a reaction uphill. Again, if we had a ball at the bottom here, where we're starting, we have a ball at the bottom where we're starting at the reactants, and we're trying to push that ball up the hill. It's going to take energy to do that. Can you do it? Sure. But you've got to put energy in. So going uphill is unfavorable because in general, you want to be able to get energy out of chemical reactions. If you have to put energy into a chemical reaction, that costs you, and that's not good. So to get that ball up to the top of the hill here, we need to put energy in. So uphill reactions, positive delta H. Why positive? Because the energy is increasing. The potential energy of the system is increasing. And since that delta H is positive, that means that we need energy in. So where does that energy in come from? Again, let's take a look at our diagram. We've got our Erlenmeyer flask, like my artwork here. Yeah, there's a reason why I didn't go into art, okay? And that's my reaction. Actually, that was my system, which is the reaction. And surrounding that, we have our surroundings. Again, together, these make up the universe. Now, remember, the potential energy of the system is increasing. Like before, conservation of energy tells us that some energy somewhere else must be decreasing. And that energy is being transferred into the system. And so this is why this is called endothermic, because the energy is going in. Again, what energy is going in? What energy is being converted to potential energy? The kinetic energy of the surroundings is going down, which means that the temperature is going down. And if you recall, Dr. Showalter in the video had the endothermic reaction literally freeze to the board when he put a little water underneath it, because it froze that water. It got so cold that it froze the water and froze the reaction to the board. In terms of numbers, to see that this is a positive number, we're going to write that the delta H, again, is equal to the potential energy of the product. Always where you end up minus where you started. Potential energy, it's like a final minus an initial, minus the reactants. And so that is equal to, final is 600 kilojoules per mole. Where we started was 200 kilojoules per mole. And you can see that that's a positive 400 kilojoules per mole. Okay, so we will make more use of this over the next day or two. But for today, make sure that you finish the worksheet based on the driving forces video, and that's your homework for tonight. All right, have a good rest of your day, and I will see you next time in class.